Let's talk about polar coordinates, section 1.3. This may be review for a lot of you, but these are some skills that we need moving forward. The goals for this section, to be able to locate points in the plane using polar coordinates, to convert points between rectangular and polar coordinates, sketch polar curves from a given equation, convert equations from rectangular to polar coordinates, and a little bit about symmetry in polar curves and equations. The big idea here is that when we're working with shapes that have intrinsic circularness, like cylinders or circles or spheres, polar coordinates are often a good choice to describe the shapes. This class is going to be a lot about describing shapes mathematically. When we're building double and triple integrals later in the semester, we need to be able to describe shapes mathematically in order to build and execute integrals. There's nothing special about polar coordinates. It's just another way of describing the plane, just like Cartesian coordinates. I think the biggest difference is probably that we've been using Cartesian coordinates for most of our lives, and we have some intuition about how Cartesian/rectangular coordinates behave. And we don't use polar coordinates very often, and so we have less intuition. So one of the things that you want to pick up in this section is a little bit more intuition about polar coordinates. Let's jump over to the textbook and just scan through the section briefly. We have the learning objectives up here. Defining polar coordinates, we essentially specify, instead of specifying position by a distance along the x and a distance along the y, we specify a location by an angle with the x-axis and a distance from the origin. The angle is given by theta, the distance is given by r. With a little bit of trigonometry, we can see, for example, that r, being the hypotenuse of this right triangle here, r is just the square root of x squared plus y squared. And theta, being the angle inside this triangle, the tangent of theta is the ratio of the opposite to the adjacent side lengths, y over x. So we have a quick formula for theta. Tangent of theta is equal to y over x. And we can solve for theta using arctan, and we get the familiar formula that theta is equal to arctan of y over x. In the other direction, if we're given polar coordinates and we want to find Cartesian coordinates, we can again use trigonometry. R cosine theta gives you x, r sine theta gives you y. Those formulas are summarized here in Theorem 1.4. One of the things that we'd like to do is be able to convert back and forth between the two using these formulas or just using our trigonometric intuition. For example, 1, 1 here, we see that 1, 1, let me jump over to my notes briefly. I would prefer that you use your intuition whenever possible. And so if we want to convert 1, 1 to polar, I almost always just start visualizing the location of the point 1, 1. I'm going to use a different scale here. Let's go out maybe here and call that 1, 1. Like that, x, y. I'm just constantly thinking about, well, what's this angle and what's this distance? Well, for 1, 1, this angle is clearly 45 degrees, aka pi over 4 in radians. And if this side is 1 and this side is 1, the Pythagorean theorem quickly tells us that this side is the square root of 2. So in polar coordinates, that is the square root of 2 pi over 4. It's our convention to always list r in the first slot and theta in the second slot, just like we always list x in the first slot and y in the second slot for rectangular or Cartesian coordinates. This is what the plane looks like under a polar coordinate system. Once again, if we want to locate for example, the exercise that we just did, the square root of 2 and pi over 4, what do? Usually I locate the angle first, pi over 4, doesn't really matter. And then I go out square root of 2. Square root of 2 is just a little bit more than 1. It's around 1.4 here. And so the 0.11 is sitting right here. So that's what the polar coordinate system looks like on the plane. As I noted earlier, it doesn't really matter. You can get to any point on the plane using either Cartesian or rectangular, Cartesian/rectangular or polar coordinates. It's just a different way of describing locations. Just like we have functions in Cartesian coordinates, y equals f of x, we also have functions in polar coordinates, r equals f of theta. We'll talk a little bit about plotting those in a minute. The fallback position for plotting something like r equals f of theta is really just to create a list of theta values and to compute the corresponding r values and plot them. But as you gain a little bit of intuition on polar curves, just like you have intuition on Cartesian curves, y equals f of x, you may begin to start to sketch them more easily. Another strategy is to take the polar form of the curve, r equals f of theta, convert it to Cartesian, and hope that your Cartesian intuition will help you plot the curve. Whether a curve is expressed as r equals f of theta or y equals f of x, it's the same curve, just different coordinates. So if you can convert from polar to Cartesian and plot, then you've successfully plotted the polar curve. They're the same. All right. Transforming equations to rectangular coordinates. So these equations are equations involving r and or theta. To convert them to Cartesian coordinates, usually the easiest thing to do is to just simply take theta, for example, and replace it with the arctan of y over x, and take r and replace it with the square root of x squared plus y squared. Then, of course, you're going to want to simplify as much as possible in hopes that the transformed equation is somewhat familiar to you. Honestly, the only reason to switch from one representation to the other is to help you identify what the curve looks like. So in each of these cases, for example, you would just replace with the Cartesian formulas. I will say the third one is a little bit interesting. So let's talk about that. R equals 6 cosine theta minus 8 sine theta. So here I have a polar equation. In fact, it's of the form r equals a function of theta. Not at all obvious what kind of curve this is, and it's not really obvious how to convert this to Cartesian coordinates. Sometimes it involves a bit of a trick or a bit of a manipulation to get the Cartesian to polar formulas to appear. And I happen to know, having worked on this a little bit before I started this lecture, that if I multiply through this equation by r squared, I get this. I just introduced a factor of r, but if you look really closely at these two factors, that's just x and that's just y. So if I'm clever, I can manipulate the polar equation so that I introduce explicitly the Cartesian conversion formulas. And r squared on the left, we happen to know is x squared plus y squared. This doesn't really tell me the particular figure, but now I can use some things I've learned about Cartesian equations and manipulate this into something recognizable. Let me show you that. X squared minus 6x, moving everything to the left-hand side, plus y squared minus 8y equals 0. And what I'm going to do is complete the square on these two terms. x minus 3 squared plus y, oops, all right, x minus 3 squared, FOIL it out, x squared minus 6x plus 9. I've introduced a plus 9 here, so I better get rid of it in order to preserve the equality. Similarly, y minus 4, quantity squared, squared out y squared minus 8y plus 16. So I've introduced an extra term of 16 here. I better get rid of it if I want to preserve the equality. Now take the 9 and the 16, move it over to the right-hand side. And I get something that should be familiar to you. This is the standard equation of a circle. The circle has center at 3, 4, and radius 25. Sorry, 5. So this is the standard rectangular equation for a circle. Definitely want to recall that, remember that, it'll come up again. Continuing our flyover, here are a few common kinds of polar curves that you'll encounter. For example, a fixed theta, set theta equal to k, that corresponds to a line through the origin with angle theta or angle k. If you see r equals a linear combination of sine and cosine, a cosine theta, b sine theta, that's a circle. It's really important that it be cosine theta, not cosine 2 theta or cosine theta over 2. It has to be cosine theta, has to be sine theta. In that case, however, though, you get some kind of circle. Here's a spiral, r equals a plus b theta. As theta grows, r grows, and so as theta grows, you get farther and farther from the origin, and that's how a spiral behaves. There are other more exotic kinds of polar curves, cardioid, limicon, rose, etc. Notice the rose here. The rose is r equals a cosine b theta. The b here controls the number of petals on the rose. So if b is 4, you'll get, if b is 2, you'll get 4 of these. It's important, however, just to remind you back here, there's no b on here. So if there's no b, it's just cosine theta, sine theta, then you're getting circles. All right, let's keep going here. You can get some really exotic and beautiful polar curves with really minor changes to the formulas. Spirals. All of these things, you'll notice, have sort of circularity in their natures. And when we encounter things with circularness later in the class, polar coordinates and other sort of circular coordinate systems are going to be helpful to us. Let me finish up this flyover by talking about symmetry. In our case, we're just talking about reflective symmetry about a line. For example, this cardioid is symmetric about this horizontal axis. In this case, we say it's symmetric with respect to the polar axis. The polar axis in polar coordinates is this horizontal axis corresponding to theta equals 0. If it's symmetric with respect to some other axis, some other fixed theta, then we say with respect to the pole. And if it's symmetric with respect to the vertical axis, we just say with respect to the vertical axis. So these are just nomenclature or vocabulary words that we associate with polar curves and polar coordinates. Not super important for our purposes here, but nice to know. All right, let's get into doing some of the exercises before I turn you loose. So I've got a collection of exercises that I want to sort of go over with you. let's talk a little bit about the first collection of exercises, problems 125 through 131. They're all pretty similar. Let me grab, yeah, I guess it's worth copying here. So let's grab this thing. All right, and in preparation for this lecture, I have a copy of a polar coordinate system here. So let me grab that, and we'll put it down here with the points that we would like to plot. All right, see if I can get this all on the same screen here for you. I think we're just about there. All right, so this is a polar coordinate system. These concentric circles are separated by 1 unit. So if we were to label them, we would have 1, r equals 1, r equals 2, 3, 4, 5, and 6, all the way out. And then along these lines through the origin, the angle is pi over 12, pi over 6, pi over 4, pi over 3, etc. If you want to plot one of these points, look at the coordinates. So r is equal to 3 in problem 125. R is equal to 3, so we go out to the third concentric circle. And the angle is pi over 6. So we're going to put 125 here. 1, 2, 3, and out at pi over 6. There's 125. Let's do problem 126 really briefly. Let's find 5 pi over 3. 5 pi over 3 is down here along this ray. This one's a little tricky because r is negative. So you're asked to move out along this direction, but a distance of negative r. And what that really means is just go in the opposite direction. In the opposite direction 2 units. All right, so this, let me just relabel here, 3 pi over 6, and this is negative 2, 5 pi over 3. So when you have negative r's, that's a signal that you don't go out in the along the positive ray, but you go back through the origin in the negative direction. So another way that we could have expressed this without the negative r would be to write, I don't know, let's see, what's a good color to use? Let's use rainbow color. So another way to write this would have been 2 comma 2 pi over 3, like that. And that's an important lesson to learn here. Polar coordinates are not unique. So there are lots of ways of describing the same location using polar coordinates. This is not true of Cartesian coordinates. Every point has a unique set of Cartesian coordinates. So there's a subtle difference there. All right, let's keep going here. We've got a couple of more problems to go over before we wrap it up. Problem 132, let's go see what that is. So problem 132 is kind of going in the opposite direction. You're given some points on the polar plane, and you're asked to give the polar coordinates of those points. So let's see what that looks like. Half the time I spend arranging my notebook here. Let's add some space, and let's grab this guy and move it into here. All right, so what are the coordinates of A? Well, I think the first thing we have to do is figure out what these angles are. We've taken the first quadrant, which goes from 0 to pi over 2, and we've chopped it up into 3 pieces. So 1/3 of pi over 2, of course, is pi over 6, and 2/3 of pi over 2 is pi over 3. So now we see that A is really just 1 pi over 6. C is out here at pi, so C is going to be 1, 2, 3 pi, like that, and so on. You can work your way around and identify the angles and then just count concentric circles to tell you what the radius should be. All right, let's carry on. Problem 140. So here, given the Cartesian coordinates, let's find the polar coordinates. So in problem 140, we're interested in converting Cartesian location 4, 3 to polar. I usually like to just start with a quick sketch to figure out where I am. 4, 3, 1, 2, 3, 4, 1, 2, 3, I'm here. And right triangles are really important in terms of moving back and forth between Cartesian and polar coordinates. So I almost always immediately draw that right triangle there. And our task, of course, is to figure out what's theta and what's r for this point. We know that this side is 3, this side is 4. R, by the Pythagorean theorem, is the square root of 3 squared plus 4 squared, which you may recognize as 5. 3, 4, 5 triangle. Theta, the tangent of theta is the ratio 3/4, right? Opposite over adjacent. So the arctan, so theta is equal to the arctan of 3/4. And the arctan of 3/4 is not a nice angle that you know, so you can just leave your answer in this form. 5 and arctan 3/4. That would be a perfectly sufficient answer. If you're curious, what is this angle? Is it consistent with sort of my understanding of the geometry? Then by all means, get out your favorite calculator. Nowadays, mostly I just use Google and ask it, what's the arctan of 3/4? And Google will come back at you and tell you, hey, that's 0.64 radians. And of course, you immediately are like, well, what is 0.64 radians in degrees? So let's see what that's all about. Let's convert radians to degrees, and let's put in 0.64. And that works out to be about 36, 37 degrees, which seems reasonable, right? It's not quite 45 degrees as we can see here. So this is about 37 degrees. We didn't have to do that for this exercise. It was just something that I thought might be helpful for our intuition. All right, let's continue. Exercise 156. 156. So, describe the graph of each polar equation. So in 156, they want us to actually figure out what the graph of r equals secant theta looks like. Now, got a couple of options here. One, you could start plotting points, but I'm going to share with you a different option, and that is, well, let me just list the two options here. So one, we could plot points, or two, we could convert to Cartesian. I keep saying Cartesian. It's the same as rectangular. And then hope we recognize it. So let's do that. Let's do option 2. All right, well, we've got to play around with this a little bit. We know that r is equal to secant theta, and that secant theta is equal to 1 over cosine theta. If you didn't know that, go back, review trig. Really important that you have the trig solidly embedded in your brain. All right, we don't really see the polar Cartesian formulas popping out at us, but we do know that we can do algebraic manipulation to help us along. And if you stare at this long enough, you'll see that if you multiply both sides by cosine theta, on the left-hand side, of course, you get r cosine theta. On the right-hand side, you get 1. R cosine theta, that looks pretty promising. That's actually x. And what we see is a Cartesian equation that we recognize. This is a vertical line at x equals 1. So without going through the pain of plotting points, rather we just converted to Cartesian / rectangular coordinates, we were able to plot this thing. That's definitely the most efficient way. It's not always possible, but it's definitely the way to go if you can pull it off. Let's try a different one. And I should mention here, you know, we've used Geogebra here in this class a couple of times to visualize things, and we can actually plot this function in Geogebra as it is here as opposed to here. And let me show you that because it can be really helpful if you're stuck on a problem to get a glimpse at the solution. One of the things I like about Geogebra, and sort of in line with my philosophy in general, is I try to use tools that are freely accessible to everyone. Geogebra is a free software package. It's accessible to everyone. And another thing that I like about it is people are able to make little Geogebra applications and share them with people. And here's a Geogebra application. Geogebra by itself doesn't really want to naturally plot polar curves, but it can be easily convinced to do so if you have a little bit of expertise. So this fellow, Magnus Carlsen, created this Geogebra application that lets you punch in the polar form of an equation and plot it directly without having to do any kind of conversion or manipulation. So what I want to do is plot this function secant of theta. It's important that you use theta when you're working here. Type the word theta. R of theta, excuse me. So apparently theta, the word, and theta, the symbol, are different here. But anyway, if you use the same variable on the left and on the right, r is a function of theta, and it's equal to secant theta, we see the vertical line that we expected. All right, we'll come back to that again in a bit. Problem 162 is a little bit harder and is going to require a little bit more work. And I'm going to just kind of demonstrate pieces of this, and then I'll jump ahead to the finished product, but this can be very time consuming. So we're looking at problem I'm sorry, I skipped ahead a little bit. 162 first. Let's talk a little bit about 162. So here we're given an equation in Cartesian form, and we're asked to convert it to polar form and then sketch its graph. Let's look at y squared equals 4x. Y squared equals 4x. To convert this to polar form, just use the conversion formulas. We know that y is equal to r sine theta, and it's squared. And we know that x is equal to r cosine theta. You could stop there, honestly, but maybe let's practice putting it into polar function form. So we'll expand this out, r squared sine squared theta for r cosine theta. We can divide out the common factor of r. And let's divide both sides by sine squared. And now we've written r as a function of theta, and indeed we could plot this thing over on Geogebra. So let's get rid of this one and replace it with 4 cosine theta divided by sine theta quantity squared. And we get something that looks an awful lot like a parabola, sideways opening parabola. Is that consistent with what we would expect? Well, if you go back to the original Cartesian form, it's actually a lot clearer what this thing should look like. It's a parabola opening around the positive x-axis. X equals y squared over 4. Right, x equals y squared over 4. We see that as just a parabola opening like this. So in terms of switching to polar in order to plot, that wasn't really a thing here. Switching to polar here, to me, I got nothing. I look at this, I'm like, that's a parabola? Wow, that's cool. I don't see that. Up here, parabola, absolutely, I'm totally good. So got to be strategic about this. If you're using conversion to kind of help you plot something, I probably wouldn't have converted this guy. If I just want to plot this thing, I'm just going to plot this. Okay, that said, later in the semester, we might be building a double integral, and maybe we're integrating over a circle, and then it might be useful to convert this to polar coordinates for some reason. Okay, let's go to the last exercise and see what we have here. Problem 174. 174. Here, sketch a graph of the polar equation and identify any symmetry. The polar equation in question here is r equals 3 cosine theta over 2. R equals 3 cosine theta over 2. Now you'd love to just call this, you know, a circle or something. Hey, there's a cosine, right? But no. This one's more complicated. The theta over 2 just really confuses things, makes things much more complicated. So I'm going to start the process of plotting points because we don't really have a grip on how to do this in any other way. And if we're going to plot points, we're going to need a coordinate system to work with. So I'm going to go up here and grab a copy of my coordinate system. Let's put it right there. And maybe move it up here a little bit. All right. Well, here we go, folks. We are going to plot selected values of theta, plot r versus theta, and see if we can't kind of figure this out. So I'll start here with a list of theta values and compute the corresponding r values. Let's start at the beginning. Theta equals 0. If we plug theta equals 0 in for theta up here, we get 3 cosine of 0, which is 3. So we can plot the first one, 1, 2, 3, right there. Let's not do pi over 12. I don't know my pi over 12s very well. How about pi over 4? So pi over 4, actually, no, I'm not excited about that one either because that gives me pi over 8, and I don't want to think about pi over 8. Let's try pi over 3. Okay, pi over 3 goes to pi over 6 here when you divide by 2. Cosine of pi over 6 is root 3 over 2, and then we have that extra 3 out front. Okay, what is 3 times root 3 over 2? Let's go check Google. Use the massive power of Google to compute 3 times the square root of 3 over 2. 2.6, give or take, 2.6. So along pi over 3, 1, 2, and 0.6. We're kind of right there. Let's keep going. Let's try pi over 2. Pi over 2, divide by 2 is pi over 4. Cosine pi over 4 is root 2 over 2. So we're looking at 3 root 2 over 2. Alrighty. What is 3 root 2 over 2? I'm just going to go back to Google. And that's 2.1, give or take. So along pi over 2, 1, 2, and a little bit, 2.1. All right, you know, we could keep going here. I'm going to jump ahead here and do a few more, and then I'll come back. All right, so while I was gone, while you were gone, I added a few extra points here. And I'm using sort of symmetry, and I'm using ideas about cosine and what I know about cosine to kind of fill in these dots. But notice when I get around to pi, for example, when I plug in pi here, I get cosine pi over 2 is 0. So there's a point here that corresponds to theta equals pi. And then when I go past, let's say go to 4 pi over 3, 4 pi over 3 goes to, when I divide by 2, goes to 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2 times 3, we get negative 3/2. So if 4 pi over 3, I need to go back through the origin out to 1.5 or 3/2. So remember, I go out here a negative distance, which means go back through the origin here. Similarly, when I got around to 3 pi over 2, that worked out to 3 pi over 4 after dividing by 2. Which is negative 3 root 2 over 2. And similarly here, when I'm down here, I go back through the origin and I land, sort of cross over the curve. If I continue, say out here at 5 pi over 3, I'm here, sort of symmetric with this. And then finally I get around to 2 pi, plug it in up here, I get cosine of pi is negative 1, that's negative 3, I'm back through the origin. And in fact, I know that there's going to be some symmetry going on the other side too, here and here and here. So what's going to happen is I'm going to go up as I continue around. I'm going to get something that looks like that. There are a couple of lines of symmetry here and here. It's easy to see when you have symmetry along theta equals 0 whenever you have an even function like this, an even function of theta. So cosine theta, you could replace it with minus theta, and then cosine of minus theta is the same as cosine of theta, so because it's an even function. And so anytime you have an even function of theta on the right-hand side, you're going to have this polar symmetry. Okay, we can verify that this is indeed the right sketch, as horrible looking as it is, by going back to the Geogebra app and really briefly kind of confirming that. Let's do that. All right, so 3 cosine theta over 2. Like that. Looks like it's kind of right, but something's going on here, and that is the person that wrote this chose a fixed parameter range. They're using parametric equations to actually plot this thing. The fixed parameter range is not really sufficient to what we want, so I'm going to go in here and start that at 0, and that kind of finishes that off. And I'm going to go out to maybe twice what the original author had, and that actually completes the figure. What happens if you go outside of this parameter range? You just start retracing the curve. It's a pretty curve. Okay. Last, not least, so everything's on the table in this section. So I want you to work on these problems, 125 through 177 in particular. Pay attention to the tricks, the algebraic manipulations that help you use the coordinate, the Cartesian to polar coordinate transformations and so forth. When you feel like you're ready, go over to WebWork and complete the assessment for section 3. Thanks.